Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, our mission is to transform some of that useless hate energy into useful love energy. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. Now let's get down to some serious math. This is our continuing video series on algebra, and this will be the second video, video number 2, and we'll get going with question D. We have 3 bracket x squared minus 2 all to the power 2, dot bracket 2x minus 3 all to the power 2. If we look inside the brackets over here, we have a quadratic because it has degree 2. And we have a linear factor, it has degree 1. And we notice that the entire expression over here is really a monomial or a cluster. It's a single cluster. The fact that we have power 2 here indicates that we should write this factor down twice. And we have power 2 here, so we should factor or write this factor down twice as well. Because after all, the mission over here is to expand the expression. 3 is an external multiplier, and we'll just drop it down for the time being until we get to the very end. So we drop down the 3, we write down x squared minus 2 down twice, and we write down 2x minus 3 down twice, and we're going to expand 2 brackets at a time, 2 brackets at a time. Over here we have 2 bullets, 2 targets, 2 bullets, 2 targets. And we're going to use the bullet target method to do the expanding. Again, we drop the 3 down. We focus on the first bullet target problem. And we have x squared times x squared, which will give you x to the power 4. And x squared dot negative 2, which is minus 2x squared. And negative 2 dot x squared, which will give you another minus 2x squared, and negative 2 dot negative 2 will give you a plus 4. Now we'll expand the second set of brackets, again using 2 bullets and 2 targets. 2x dot 2x is 4x squared, 2x dot negative 3 is minus 6x, minus 3 dot 2x is minus 6x, and minus 3 dot minus 3 is 9. The idea now is to look inside each set of brackets over here and collect like terms. The 3 gets dropped down because it's the external multiplier or the external coefficient. X to the 4 gets dropped down because it's the only term of its type. It's the only quartic term. And over here minus 2x squared is minus 4x squared, and 4 just gets dropped down. 4x squared gets dropped down, and minus 6x is minus 12x, and 9 just gets dropped down. We identify the quantity inside this set of brackets over here as a quartic polynomial. It has degree 4, and this is a quadratic polynomial of degree 2. And we have 3 bullets, 3 targets. And again, the multiplier is on the outside and it will remain on the outside until the very end. The idea now is to use these 3 bullets to fire at these 3 targets. And so we use a BB.TTT. And that's what we're going to be doing in the next step. The 3 gets dropped down. X to the power 4 dot 4x squared is 4x to the power 6. X to the power 4 dot minus 12x is minus 12x to the power 5. X to the power 4 dot 9 is minus 9 or plus 9x to the power 4. And then we're done with the first bullet. We turn our attention to the second bullet. Minus 4x squared dot 4x squared is minus 16x to the power 4. Minus 4x squared dot minus 12x is 48x to the power 3. Minus 4x squared dot 9 is minus 36x to the power 2. And we're done with the second bullet. Let's turn to the third bullet. 4 dot 4x squared is 16x squared. And 4 dot negative 12x is minus 48x. And 4 dot 9 is 36. and we've exhausted the third bullet. At this stage over here, we continue to drop down the 3, and we're going to use backward bin gathering to gather up like terms. The highest power is x to the power 6, so we start off with x to the power 6, and we scan the expression for only x to the power 6 terms, and we pick up a 4, drop it inside the bin, then plus x to the power 5 dot, put an empty bin, and we scan for x to the power 5 terms, we pick up negative 12, drop it inside the bin, and there are no more x to the power 5 terms, so we close up the bin. Then a plus x to the power 4 dot empty bin, we scan for x to the power 4 terms, we pick up a 9, and we pick up minus 16, and we close up the bin because we're done with x to the power 4. And then plus x to the power 3 dot empty bin, we scan for x to the power 3 terms, we pick up a 48, drop it inside the bin, and close up the bin. There are no more terms. Then plus x squared empty bin, we scan for x squared terms over here, pick up minus 36, and then plus 16, and close up the bin. Then we scan for linear terms, x to the power 1. We scan and we pick up minus 48, drop it inside the bin, and close it up. We're done with x to the power 1. And finally, we open up a constant bin, scan the entire expression for constant terms, and you pick up a 36. Okay? Do not forget, when employing the backward bin process, that is to say BBG, in between the bins, always use a plus sign. Plus sign, plus sign, plus sign, plus sign, plus sign, and plus sign. Okay, don't forget to do that, because otherwise you will start making sign errors for sure. Okay, all the negative signs, if there are any, will be inside the brackets, inside the bins. Okay, you can think about these as collection bins. Okay, the negative signs will all be inside the collection bins when there are negative signs. So again, we drop down the 3, and all we have to do is simplify at this point. We get 4x to the power 6 minus 12x to the power 5. And over here, 9 minus 16 is minus 7x to the power 4. And then we get a 48x cubed. And minus 36 plus 16 is minus 20x squared. And we get minus 48x. And then finally, plus 36. And at the end, and only at the end, will you release the 3. Had you have released the 3 way like anywhere else, like for example, we could have released the 3 over here, we would have created a catastrophe because all the coefficients would increase by a factor of 3. And you would have had a big mess over here because the numbers would have become quite large. So there's no point in doing that. Release the external coefficient only at the very end. At this point right here, do we do the release? So we have a bullet over here, and we have a bunch of targets over here. Okay, specifically we have 7 targets. So when we release the 3, we multiply all the coefficients by 3 to get 12x to the power 6 minus 36x to the power 5 minus 21x to the power 4 plus 144x to the power 3 minus 60x to the power 2 minus 144.x, and finally plus 108. And that will constitute the final answer, or the expanded form of this factored form up here. And again, we emphasize that in terms of utility, the factored form from a mathematical standpoint will yield much better information than the expanded form will ever yield. Okay, so the rule of thumb, do not expand unless you have motive, unless you have reason for expanding. Otherwise, do not expand, because the expanded form is a big mess in and of itself. It's a polynomial of degree 6, and there are 7 terms altogether. Whereas the factored form over here, it's very easy to find the zeros of this factored form if that's what we want to do. We can find dominant terms, etc., etc. Okay, there's all kinds of things we can do with a factored form, which is quite a bit more difficult to do with the expanded form. Okay, let's turn to the next slide. And this question over here is very similar to the last one, except we see we have two clusters. The separator is the minus sign. So we have x plus 2 to the power 2, that's a perfect square. X minus 1 to the power 2, also another perfect square. X minus 1 to the power 2, perfect square. X plus 4 to the power 2, also a perfect square. And the inside of the brackets over here are all linear factors. Now, instead of writing because we have so many perfect squares in this expression, it's easier to use the perfect square expansion formula. If you expand a plus b to the power 2 by writing it down side by side twice and using a bullet target, we easily get a squared plus 2ab plus b squared. And what does that tell us? That in order to rapidly expand a perfect square, you just square the first term, you take the product, a dot b dot 2 for the middle term, and you square the last term. So again, you square the first term, you take the product, a dot b dot 2 for the middle term, and you square the last term. That's the easiest way to do a perfect square. Otherwise, you're doing way too much work. Okay, so let's see how that works out. You square that, you get x squared. You do x dot 2 dot 2, you get 4x, and you do 2 dot 2 is 4. Easy to do. X dot x is x squared. X dot negative 1 dot 2 is minus 2x. Minus 1 dot minus 1 is 1. The minus sign comes from the separator. We'll do x dot x is x squared. X dot negative 4 dot 2 is minus 8x. And negative 4 dot negative 4 is 16. And then finally, we have x dot x is x squared. X dot 4 dot 2 is plus 8x. And 4 dot 4 is 16. Again, we have two clusters. That's never going to change. Over here, we have 3 bullets and 3 targets, and 3 bullets and 3 targets. The minus sign is on hold. Okay, so let's go and do the bullet target process. We'll do the first cluster first. X to the power 2 dot x squared is x to the power 4. X to the power 2 dot minus 2x is minus 2x cubed. X to the power 2 dot 1 is just x squared. And 4x dot x squared is plus 4x to the power 3. 4x dot negative 2x is minus 8x squared. And 4x dot 1 is just plus 4x. Then we have the separator. Okay, the separator is the minus sign. I put it down here in the next line. And we don't worry about the minus sign until the end. Over here we have x squared dot x squared, which is x to the power 4. X squared dot 8x, which is 8x cubed. X squared dot 16, which is 16x squared. And then minus 8x dot x squared is minus 18x squared. Minus 8 dot 16 is minus 64. Minus 8 dot 16 is minus 128x. And then I think we're done with that. And we go to the last bullet. 16 dot x squared will give you 16x squared. 16 dot 8x will give you 128x. And then 16 dot 16 will give you plus 256. Okay, now what we can do at this stage is we can backward bin the entire mess over here. We can use backward bin gathering to collect like terms for the entire mess. Okay, if we look at this expression over here, we have a polynomial of degree 4. Polynomial of degree 4. Okay, so the highest power is x to the power 4. And we begin the BBG process by opening up an x to the power 4 bin. Then we scan. We pick up a 1 here and a minus 1 here. So we get a 1 minus 1 inside the x to the power 4 bin. Then plus x to the power 3, and then put down an empty bin. Over here we pick up negative 2. Over here plus 4. And then over here minus 8. And then over here plus 8. I dropped all those numbers inside the bin. Then you open up an x squared bin. And you scan and drop. The x squared term over here, you pick up a 1. The x squared term, you pick up minus 8. The x squared term, you pick up a 4. and then you go down here, you pick up minus 16. You're essentially bringing that minus sign in there with your eyes visually. So you pick up minus 16, and then you pick up plus 64, and then finally you pick up minus 16 again, and you close up the x squared bin. And then we continue on the next line. We open up a linear bin, so plus x dot empty bin. You know, make sure you make the bins wide enough to be able to hold all the coefficients. And now we scan for linear terms. We pick up a 4 here, minus 8 here. We drop them in. Over here, we pick up 128, minus 128, and we drop them in. And we close up the bin because we're done with the linear terms. And finally, the constant term. The constant term over here is 4, drop it inside. And the constant term for the second cluster is minus 256. Okay, so at the end, all you do is simplify each bin. 1 minus 1 is 0. 0 times x to the power of 4 is just 0. So the quartic term does not appear. Over here, if you simplify this bin, you get a 2x cubed. And if you simplify this bin over here, we'll get a 29x squared. Simplify this bin over here, we'll get a minus 4x. And simplify this bin over here, we'll get minus 252. Okay, so at the end of the day, we get a cubic polynomial. The degree is 3. The coefficients are 2, 29, minus 4, and minus 252. Originally, we thought we had degree 4. You see x to the power 2 dot x to the power 2 is x to the power 4. Then x to the power 2 dot x to the power 2 will give you x to the power 4 again. But the leading term over here, so the leading term over here is x to the power 4. Leading term over here is x to the power 4. X to the power 4 minus x to the power 4 will give you 0x to the power 4. And that's why the final answer is not a quartic. Okay? So let's go on to the next question. Q7 is about factoring. Okay, so we're going to introduce you to factoring. It says factor each of the following expressions completely. So before we proceed, factoring is the inverse of expanding, and factoring requires a lot more thought than expanding. Anything in math proceeding in the inverse direction usually requires considerable more thought and ingenuity than proceeding in the forward direction. It's sort of akin to picking up a glass and breaking it. If you pick up a drinking glass and you break it on the floor, that's akin to that's similar to a forward process in math, and the inverse process is to pick up all the pieces on the floor, glue them all back together to produce the original glass. You'll agree that it's much more difficult to disassemble, or it's much easier to disassemble a puzzle than to put the puzzle back together. Okay, and that's what happens with forward and inverse processes in math. Okay, so factoring is an inverse process, requires more thinking, more strategy than expanding. So let's go ahead and if you look at this question over here, part A, we have two terms over here. You can think of them as two clusters, if you will. The separator is the plus sign. We'll refer to them as two terms for the time being. There are no brackets or anything like that, so they're monomial terms. And the idea over here when you're factoring is to look at the coefficients first, 12 and 18, and you conclude that the greatest common factor is 6. So look at the coefficients first. The greatest common factor of 12 and 18 is 6. It's the biggest number that divides evenly into both coefficients 12 and 18. Then you look at the variables involved. The variables are m and n. Let's scan for the lowest power of m. We have m squared here and m cubed here. The lowest power of a variable will be part of the GCF. So we tack on m squared to the GCF. Then we look for the lowest power of n appearing. The lowest power is n squared. We tack that onto the GCF. So essentially, we're slowly building up the GCF. The entire GCF is 6m squared n squared. The next step is you put the GCF out front, and our job is to find the balance now. To find the balance, what we're going to do is do the GCF divided by the term. Or sorry, the other way around, it's the term divided by the GCF. So the divisor is always the GCF. The dividend is always the term. Okay, the divisor is the GCF, the dividend is the term. So inside the brackets, which I call the balance, 12 divided by 6 is 2, put it down, m squared over m squared. The m squareds cancel, so there's no m in there at all. N cubed over n squared will just give you an n. Then we do 18 divided by 6 will give you 3. M squared over m cubed over m squared will give you m. And then n squared over n squared will just give you 1, so it doesn't appear. Okay? And so this will be the factored form. The GCF is on the outside and the balance is on the inside. And you can't factor this any further. So that's a typical example of factoring out a GCF. The next thing over here is a trinomial. The degree is 2, so it's a quadratic. Function. Consists of 3 terms, trinomial. There is no GCF. If you look at the coefficients, 1, -9, and 20, there is no GCF. And there is no lowest power of x appearing in every term. Okay? So we identify the coefficients in front as ABC. And the coefficients in this case are 1, -9, and 20. And now, because this video series is not entirely on factoring, it wasn't meant to be entirely on factoring. There are little tidbits here and there. I teach students how to actually use their EQN button on their calculators to either solve quadratics or cubic, either solve quadratic equations or cubic equations, but it's a little trick I picked up that you can actually use your calculator to factor trinomials of this type. Okay, so I'm not going to go into details, but that's why I put down use EQN3, because EQN3 is a button on the calculator which will solve quadratic equations. Okay, so that'll help you factor. But anyway, the factors are x minus 4, x minus 5, and then you can verify. If you do a bullet, target on this, you expand, collect like terms, you'll get the original. Okay, you'll get the original quadratic. So again, I'm not going to go into details. FF just means factored form. I'm not going to go into details. I'll go into details of factoring trinomial expressions in another video at some point in time. Okay, so let's look at the next one. Again, we recognize this is a trinomial, and it's a quadratic because the degree is 2. And it's 3 terms. The GCF this time, 3, 24, and 45. The GCF is 3. So we can factor out the GCF out front and use division to find the balance. We get 3x squared divided by 3 will give you x squared. 24x divided by 3 will give you 8x. 45 divided by 3 will give you 15. And now if you look inside the brackets, we notice the coefficients ABC are 1, 8, and 15. And again, you can use this EQN3 button on the calculator. Maybe one day I'll make a video with a calculator showing up on the screen so you can learn how to use your calculator to actually do trinomial factoring. But it's very easy to do if you know what you're doing. So, that's for a future video. Anyway, what you want to do over here is drop the 3 down. It turns out that the factors are x plus 3, x plus 5. If you re-expand this using 2 bullets and 2 targets, you'll certainly get x to the power 2 plus 8x plus 15. So you declare this to be the factored form. We have a coefficient out front and 2 linear terms that are multiplying each other. and that constitutes a factored form. I think I'm going to do an over and out for this video. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, tell us how to improve it. Over and out for Math Lab Tutorials in Toronto.